All right, thanks, Luke, and thanks for giving me the opportunity today to speak. Can you hear me okay?
Sounds good to me.
Great, thanks. So, as Luke said, I'm going to be speaking today about a E3SM ecosystem project, a SIDAC project called DEMSI, the Discrete Element Model for Sea Ice. And first off, how do I make it go down? Oh, okay. First off, I just want to say this is a joint project between Los Alamos, Sandia, and the Naval Postgraduate School. And so here at Los Alamos, we have myself, Andrew Roberts, and Min Wang. And then at Sandia, I have Cara Peterson, Dan Bolintinenu, and then previous members of the project who have moved on to other things are Paul Kuberry and Dan Ibanez. And then at Naval Postgraduate School, we have Travis Davis, a master's student there that's doing some related work to DEMSI. So, okay, so the aim of this SIDAC project is to develop a discrete element method sea ice model suitable for global climate applications. And there's two kind of big reasons why we propose this and we want to include this into E3SM. One is that we hope this new model will have an improved representation of sea ice dynamics, so better sea ice dynamics fidelity, and also hope that by using a particle method, we'll have improved performance on future DOE heterogeneous computing architectures that are being built at the moment with their GPUs and whatnot. So DEMSI is a particle method, and it uses a discrete set of elements which represent regions of sea ice. And within the model, the idea is to explicitly calculate forces between elements and then integrate the equations of motion for each element. And this is certainly not a new method applied to sea ice. Mark Hopkins from Corel has done a lot of work on a polygonal Voronoi-based discrete element model for sea ice, and Herman as well has done a lot of work in this field. But our ultimate goal is to make a model that is suitable for inclusion in a global climate model, which is a bit different to the aims of previous work. So this project is part of a SIDAC project, Scientific Discovery Through Advanced Computing funding call. And the aim here is that it combines researchers from ASCA and from domain science in order to bring those two sets of people together to produce new and exciting things. And so part of this recent round of funding for SIDAC in relation to E3SM, two major projects were funded. One of which is Kanga, which aims to produce new methods for coupling, and the other one is related to the land ice. And also 6 pilot projects were funded with the aim of building new components and new modeling features for E3SM for the long term, for like version 4. And the point of these projects is they're meant to be high risk and high reward, and I think I will convince you today that my project is certainly high risk. So DEMSI, it's funded at $3 million for 2.5 years, with the possibility of a continuance for a further 2.5 years. Yeah, and the aim of all these projects is to develop new components for E3SM. So what are the scientific goals of this project? Well, current models of sea ice generally treat sea ice as a viscous plastic continuous material. And this rheology assumes that grid cells are large enough that there's an isotropic distribution of leads within each grid cell. And these kind of models were developed when resolutions were much larger than they are now, and as we've moved to much higher resolution, so in our high resolution E3SM simulations, the sea ice model has about 6 kilometer resolution in the polar regions. It's not clear that these viscous plastic rheologies are appropriate for those very high resolutions where it's probably no longer true that a grid cell has a nice isotropic distribution of these leads within it. So yeah, also observations suggest that these VP models don't do great below about 10 kilometers. And this comes from sort of deformation scaling analysis, and also the dispersion of GPS buoys tend to disagree with a viscous plastic rheology. So the advantage in this regard of a discrete element method is that it allows us to explicitly determine complex force laws between elements, and with that we hope to capture better the sort of anisotropic, heterogeneous, and intermittent nature of sea ice. And some of the things we're going to be explicitly simulating, for instance, are like the explicit fracture and breakup of the pack. So DEMSI, as I said, Mark Hopkins did a lot of work with polygonal elements, but for our work, we're going to start off with circular elements, since it's more computationally efficient, and see how far we can get with that. Also because climate scale resolution is going to be larger than the flow size. Our elements represent regions of sea ice and have their own ice thickness distribution. The dynamics of DEMSI is provided through the Sandia National Laboratory's large-scale atomic molecular massively parallel simulator, or LAMPS, which is a molecular dynamics code developed at Sandia, which has built-in support for discrete element modeling, including the history-dependent contacts, which are needed for modeling sea ice. And it's very computationally efficient. A lot of work has gone into making it massively parallel and to scale efficiently. For thermodynamics, we have the CICE Consortium Ice Pack library built into DEMSI, which is a state-of-the-art thermodynamics package that is currently used in E3SM in version 0 through CICE, and also in version 1 through MPAS Sea Ice. So it's really a state-of-the-art thermodynamics package. So what are the principal challenges of building a discrete element method sea ice model suitable for climate applications? Well, I think there's really four main areas of challenge. The first one is related to the contact model. So how do we determine how elements should interact with one another in order to represent realistically sea ice physics? And this is made more challenging by the fact that our elements are much larger than the flow size. So we have to consider that upscaling from the flow size to our element size. Element distortion. So when sea ice converges because of wind forcing or ocean forcing, what happens is you have a formation of pressure ridges, which is effectively the conversion of sea ice area into thickness while volume is conserved. And what this ultimately means for a discrete element sea ice model is that elements are going to get smaller during this process as they get thicker. And the time step of the model is dependent on the size of the element. So as elements get smaller, the time step is required to go down. And so if we just let that carry on unabated, the simulation will grind to a halt. And so we need to do something about that. Another big issue is how we add new elements. So as the ocean cools and Frazil ice forms in it, that ice needs to be added to our element distribution. It's a non-trivial problem. Also, how do we couple our Lagrangian particles to the rest of the climate system, which is still built on a Eulerian mesh? How do we do that conservatively and monotonically, and other issues related to that? And finally, just how do we make this model fast enough that it will be suitable for the long time integrations of E3SM? So, as I said, the contact model determines normal and tangential forces between elements, and these forces, as well as the body forces, such as from forcing, wind forcing or ocean forcing, are integrated to determine the velocity. And we are going to be considering two situations, one where elements are bonded together, such as you can think of this as them being frozen together, and then at some point they'll break apart and elements will then no longer be bonded together. And so our initial implementation of a contact model basically an adaptation of the work of Hopkins I mentioned previously, but adapted for our circular elements. And so we just think of each element as having a linear bond between each element, and then each point on the bond has a viscoelastic glue, and relative motion of the elements places each part of the bond in normal and tangential displacement, generating a force and a torque. And then if that force and torque, if the stress at that point gets too large, then a crack forms from either end and propagates inwards until the two elements break apart. And the fractional law we've been using is a more Coulomb one. Once they fractured, go away. Once they fractured, so we have a situation of unbonded elements, and they have no strength in tension anymore once they fractured. But on compression, above a certain stress, they'll undergo ridge formation, where element area, as I said, is converted into thickness. And our model here is again based on the work of Hopkins, where the ridge force is given by a normal friction term, which is independent of the relative element velocity. And that's represented here in this sort of dashpot and spring diagram, where this friction slider here represents the formation of ridges. So this contact model has been validated in a number of test cases. So the elastic bonded part has been validated in a cantilever test case against analytical solutions to it. And the fracturing part has been tested in a number of test cases, such as this one here, where a square domain piece of sea ice undergoes a uniform divergent stress, and the thing fractures and breaks apart into kind of these large areas. We're also working to, so while that's been implemented, that model, and we're testing it at the moment, we're also working on improving upon that contact model in sort of two major ways. The first is by performing very high resolution flow resolving simulations, with the idea that once we have these flow resolving simulations over a relatively small scale done, we can use the results of that to sort of average over them and derive a contact model appropriate for our lower resolution climate-based simulations. And the other thing we're doing is work that Travis Davis at MPS has been doing, is to use lamps directly to simulate the individual formation of ridges, and use this to guide our development of a contact model. And there's a little figure here, you can see there's two sheets of thin sea ice that are being made to converge, and they fracture and break up and form this pressure ridge. The next major challenge is how to couple DEMSI to the atmosphere and ocean, to the rest of the coupled climate system. So we need a method of interpolation between our Lagrangian particles and Eulerian grids. And so we've developed a moving least squares method over at Sandia for interpolating particle data from our particles to a grid and back again. And while at the moment this doesn't conserve, which is obviously an important thing to do in a climate model, work is being done to implement optimization-based strategy to allow preservation of quantities in this remapping that are important, such as conservation of traces and matter, and also ensure monotonicity and other properties. And so these figures here just show some testing of that moving least squares interpolation method, where we have a load of particles that have some some value on them, and that's interpolated to a fixed grid here. And the error on that is displayed in this figure here with increasing grid resolution, and we get the second order convergence of the method that we expect. So yeah, that area of work is going quite well. Another big challenge is the creation and destruction of elements. So as I said, conversion of sea ice forms a pressure ridge, and this results in our elements getting smaller and the time step going down, and also potentially adds an artificial strain into the pack because of our use of circular elements. And there are a number of ways we could ameliorate this issue that we've thought about. We could use elliptical elements, move to using polygonal elements, merge elements together that get too small, periodically remap elements back to a good initial distribution that doesn't have small elements, and finally transfer mass between elements that are ridging in order to keep them the same size. And so what we've been working on is another issue related to this is Frazil formation. So so we have the ocean become cooling and Frazil ice forming in it that needs to then be added to our sea ice model. And you can see this pictorially up here. We have an initial distribution of elements and some Frazil from the Eulerian grid that we need to add. Some of that needs to be added to existing elements, shown here in blue. Other ones need to be created new. New elements need to be created to take that Frazil. And the challenge here is to create these new elements in a tightly packed configuration without disturbing the existing elements. And so our initial solution to these problems we've been exploring is a remapping of the element distribution back to an initial good element distribution periodically. So we have a geometric version of this implemented that's shown in these two figures here. We have 5,000 elements in a vortex wind field, and so the elements are all sort of moving around in this direction. And then after a certain time, that distribution of elements is remapped back to the initial square lattice of elements you can see here. That's done in a conservative way. Later on, we'll use the moving least squares coupling system being developed at Sandia to do this.
Adrian, can I ask a question about that one?
I think we're waiting to the end for questions.
Okay.
So finally, computational performance. So global climate simulations are computationally expensive, and DOE's next generation of computers are going to have heterogeneous architectures. Oak Ridge's Summit has GPUs, as is going to NERSC's Perlmutter. And so one of the tasks we're performing is converting the lamps, modifying lamps to include the COCOS programming model, which we hope is going to allow good performance on both CPUs and GPUs going forward. Also will be a sort of method used in the discrete element modeling community to improve computational performance is to artificially reduce the stiffness of elements in order to increase the time step, and so we'll investigate whether that's possible to do without affecting the fidelity of simulations. And so a big thing we're working on now is combining all of the above into trying to perform realistic basin scale simulations. One of the big challenges here is the generation of a good initial particle distribution. So you don't want all particles to be the same size, because if you did, they would just form a hexagonal close packing, and you would have 3 preferred directions in the element distribution, and you'd probably get cracking just along those preferred directions, and that's undesirable. at the same time, you want your so you want a range of radiuses of your elements, but you want them to be tightly packed, but you also don't want them to overlap initially. And so we've been looking at several methods to generate initial particle distributions. We've also worked on generating forcing data files and domain data files, and you can sort of see some examples here of initial conditions for Arctic basin simulation. And so we're working hard to get this ready to work. Another significant part of the project is to develop metrics that allow us to assess the model fidelity. So we need to demonstrate that DEMSI increases the fidelity of the sea ice dynamics. So a significant part of the project is developing new metrics that do that. We're developing a emulator for DEMSI that emulates ISAT2 thickness observations. We'll also be looking at spatial and temporal deformation scaling of the simulation results, and a buoy dispersion analysis. Of course, with the particle method, a buoy analysis is actually pretty easy because each of our particles is effectively just a buoy itself. And also looking at other standard sea ice metrics. So this is just the final slide. In terms of future work, we're currently in the process of writing a renewal proposal for DEMSI for phase 2. And our ultimate goal of phase 2 is to couple DEMSI into E3SM and to perform coupled climate simulations with it. So there are several things that need to be considered here. We need to carefully consider how we'll conserve quantities when coupling with the rest of the model, and also how we define coastlines, which has implications for conservation. We'll be looking at using machine learning techniques to further develop better concept models for sea ice, and also working on improving performance on GPUs. Another thing we'll be doing is exploring the performance advantages of DEMSI for large numbers of traces. So as a particle method, DEMSI doesn't have a transport scheme, doesn't need a transport scheme, since all the traces just ride around with the particles. And so we'll be looking at, so in the future, or at the moment, we have the desire to use the sea ice biogeochemistry capability in the model, which adds a lot of traces. And there are future developments coming to sea ice models that are likely to increase the number of traces. And so we'll be looking at how the sort of a performance advantage of DEMSI versus more traditional models in that regard. And finally, at some point in the project, DEMSI, like the rest of E3SM, will become publicly available through GitHub. And the repository at the moment includes not only the code, but also pre and post processing scripts, documentation, a whole testing system, and a whole series of test cases that come out of the box with the model. Okay, and I think I'll leave it there.
Thanks,
Hey, Luke.
Thanks a lot. Sorry, I was muted. Any questions?